Oh. Dear colleagues, today is one important day in Republic of Moldova. We start Symposium NANO 2019, where participate scientists from all over the world, from 15 countries, and in our meeting participate representative of the Ministry of Education, Culture and Research, Republic of Moldova, Tatiana Mararo, Vice-President of Academy of Sciences of Moldova, member of Academy of Sciences of Moldova, Svetlana Kazakarov, permanent representative of Germany in the European Union, Ortwin Schulte, First Secretary of German Embassy, Herr Uli, Director of Россотрудничества, First Secretary of Russian Embassy, Mikhail Davidov, representatives of ministries, departments and offices presented in Moldova, and as I told, scientists and Humboldtiana all over the world. The year 2019 has two special dates. 250 years birthday of one of the greatest humanists of the world, Alexander von Humboldt, and 150 years of the periodic system of elements discovered by Dmitry Ivanovich Mendeleev. And these two great personalities worked in Germany and in Russia, but the results of their great achievement belong to the whole world mankind. With the support of Humboldt Foundation, we organized the international conference Humboldt Kolleg SPINTECH-NANO-2019, demonstrating the long life of the humanistic ideas of our great patron Alexander von Humboldt. I would like to mention that Moldova is a small country, but it is nearly 40 Humboldtians in Moldova from all areas of science, from physics to archaeology. It is one evidence that science traditionally in Moldova was very good developed. I would like to say that 68 countries Humboldtiana are presented from 68 countries, and percentage to the population in Moldova, to the Humboldtians to 1,000 population is one of the highest in Europe. That's why we organize such meeting to promote these ideas and to attract attention of young scientists to this very good and very humanistic program, which was started again in 1953, and since then more than 30,000 brilliant researchers became Humboldtiana. I believe that after this Humboldt Kolleg, new young people will apply for Humboldt Aufenthalt in Germany. The main with support of Alexander von Humboldt Foundation, we organized this conference. And the main goal of the conference is to bring together professors, lecturers, researchers, students, and PhD students from various universities and institutes working in an intensive cooperation to share their experience, new ideas, and different forms of collaboration for development of modern forms of research and education. 4 working days of the conference give nice opportunity for group discussions and intensive interaction among participants, and as I told, to initiate new projects for more extensive collaboration. Well-known experts in nanoscience and nanotechnology from 15 countries: Germany, Great Britain, France, Poland, Sweden, Netherlands, USA, India, Turkey, Israel, Russia, Belarus, Ukraine, Romania, and Moldova are meeting together in Chișinău at this nano-symposium. Such representative forum is a clear evidence of the achievements of Moldovan researchers in the area of nanoscience and nanotechnology, recognized by the international society. As the director of Nano 2019, I wish you a successful work, useful and enjoyable stay in Moldova. Now let me give the floor to representative of our Ministry of Education, Culture and Research, Donna Tatiana Marara. Татьяна, там включить микрофон.
It is a great pleasure for me to come and to address the warmest welcome message of the Ministry of Education, Culture and Research. The conference Nano 2019 is a real evidence and proof of the fact that our researchers, scientific community has achieved big progress in the way of spreading excellence in research. Well, this is also the good opportunity to congratulate the Institute of Electronic Engineering and Nanotechnologies, the Bibliotecii in Chișinău, to having organized such an important conference dedicated to this field and bringing together well-known experts from over 15 countries in the world. I would like to mention here that one of the biggest tasks of our ministry is to elaborate policies that give opportunities to get more involved in the not only in the European research area but in the global research area. One of the ideas, and all of our researchers community know, is that in 2012, Republic of Moldova, as a partnership country, became member of the first, for us, but it was already the 7th framework program of the European Union in research and innovation. And in 2014, it was the second step, an important one, of getting more involved in the European research area and getting member and signing the association agreement to Horizon 2020. I would like to assure you that the Ministry of Education, Culture and Research is continuing to getting more involved in this research European area and preparing all steps to get associated to the next program of research and innovation in the European Union. At this stage, I would like to mention that our ministry cares about the spreading and widening excellence in research and getting more involved in the European and international research areas. And recently, the government adopted the National Program for Research and Innovation for 2020. And I would like to mention that there is an strategic direction dedicated to nanotechnologies field. Well, I think that this is a good result for our ministry to support the entire and to giving the possibility to all scientific activities to also important necessary one for our thank you.
Thank you. Let me give words to President of the Academy of Sciences, member of the Academy of Sciences,
Thank you. Dear academician, Professor dear SPINTECH-NANO-2019 conference participants, excellencies, distinguished guests. It is my honor and my pleasure to welcome you at the opening of this important conference in our country, in Chișinău, in the library of I would like to say the Academy of Sciences of Moldova, but it belongs to the Ministry of Education, Culture and Research, but nothing will change substantially. I would like to say that the Institute of Electronic Engineering and Nanotechnologies continues to impress us with their scientific results and achievements. It firmly occupied the leading position among research institutions in our country, especially in the domain of international collaboration. And this conference is an additional argument to complete this position. As it was mentioned before, there are participants from many countries, and it was very interesting very amazing to come here and to hear our discussion in different language. I invite this occasion to welcome, especially welcome the participants who came from Germany, France, Sweden, United States of America, Israel, and many other countries. The list is really long, and I apologize. I skip some of them. The second important thing in this conference is the summer school, which will be held immediately after the conference will be finished. It is not a secret that the scientific career or research career in our country, it is not very attractive conference topics to attract, to serve as a network for young people to join the research. Finally and traditionally, I would like to wish you to enjoy your stay in Chișinău, to enjoy this pleasant, beautiful autumn, to have critical discussions and meetings, to establish new contacts and new collaborations. Thank you.
Thank you very much. And now let us start our work. The first presentation will be done by Dr. Schulte. Reichsleiter Gesundheitsständige Vertretung der Bundesrepublik Deutschland bei der Europäischen Union. Please.
Thank you very much, Anatoly, and thank you for organizing this important event. I have to make one important disclaimer. My knowledge of nanotechnology is very limited. I'm a simple lawyer doing health policy at the permanent representation of Germany to the European Union. But in my former career, I was at the Federal Ministry of Health, responsible for bilateral relations, and that's where our intense and long-standing cooperation program with Moldova started. And what I wanted to do, also in the spirit of the scientific cooperation you mentioned earlier, is just to give some impressions about the 10 years of intensified cooperation and the prospects developed thereon. Let me perhaps first say we had a 10 years program for young and talented medical doctors coming to Germany. Especially glad to see that Svetlana and Ludmila and Roman are here, and many others also have been in Germany, and that many of them have undertaken impressive academic careers also at German and Swiss university clinics, and that's really something where we can build upon. As I said, Moldova was one of the focus countries of German bilateral health cooperation, and this is based on a bilateral health agreement, and it's important to note that Germany currently holds only 10 bilateral health agreements with, at the moment, with France, with Poland, with the Czech Republic, with Russia, with China, with Ukraine, Moldova, Georgia, and Armenia. And this selection also is an expression of priorities in cooperation, and we have also used it in the ministry with a view to direct also something for the budget planning to it. And one instrument we have from health agreements also is that political leaders from both sides are meeting once a year and discussing priorities, and everyone who knows ministries and administrations knows that the yearly meeting is an important precondition for success, because it's the thing where everyone is tempted to do something. Also, it is the case that not every bureaucracy when it comes to international cooperation projects is lifted by bilateral health agreements, but things are getting a little bit simpler. For instance, the Federal German Agency for Labor has a certain privileged status to all the people coming in the framework of such an agreement. There's still a lot of red tape to be undertaken, that's clear, but it's a little bit simpler. When it comes to the forms of cooperation. I think the most prominent one is the exchange program we have for medical doctors. We try to focus on such candidates which seem to have a motivation to return at some stage to their home country and to improve the situation there. We have been fairly successful. We are not successful in any case, but this is always like an international cooperation. Things change while being abroad, and biographies change, and so this is something which we take on board. It's a medical doctors exchange program. It's for the time was Moldova not an exchange program for medical professions outside medical doctors, especially for nurses. If you are following German news, you might know that the German Minister for Health is traveling across the world just to motivate some people, sending nurses and caregivers to Germany, but Moldova, as it's a state with an own lack of qualified personnel, is not a target state. We currently have Mexico and the Philippines and Kosovo, which have agreed to follow those programs. One thing, as I said, which often is a little bit of a challenge, is to assure that appropriate point for returning to the home country, and of course many influence factors are to be taken into account, like for instance mutual recognition of qualifications and diploma, but also of course forms of wage differences, and this is still a challenge to be done, but I can say that doctors from Republic of Moldova are working at the most renowned German university clinics, and if I think, for instance, at University of Hanover, being world famous for transplantation, having had a Moldovan doctor as a deputy for a longer time, this is really something we can build upon. Exchange should lead to institutional partnerships, and we have a lot of these hospital partnerships, mostly I would say with university clinics and with clinics which are run by churches and welfare organizations. It's not so much a thing for the private for-profit hospitals, because private for-profit hospitals are normally looking very much on the penny and the return on the investment, and there's another tradition in university clinics, and that's why we were quite successful in liaising some university clinics from the new federal states coming after German unification, and having also some experiences in system transformation. The densest partnership we have is certainly with the University of Leipzig. University of Leipzig has many projects of cooperation, and this morning at breakfast I could meet some representatives from the Moldova Institute in Leipzig. Leipzig is a university which has an institute which is occupying itself mainly with Moldova, which is running many programs in the field of civil society and also in the field of health. And I was glad to hear that still something is ongoing, which I didn't know until now. It's a palliative care cooperation project. Other fields were also curriculum development and problem-oriented learning as an exercise to improve teaching at the Medical and Pharmaceutical University of Chișinău, and as mentioned by the representative from the Ministry of Research, also Horizon Europe gives some important opportunities to liaise and also to find generous funding. There's one downside to it, because you certainly know that Horizon Europe projects in the EU administration are not easy in terms of bureaucracy. You have to do a lot of work before getting, but my neighbor Anatoly is experienced and glad that he's also often in Brussels, and then we can exchange on these questions. So we are also motivating the medical university to enter into this Horizon Europe business, knowing that it's a long and winding road until you get something, and you have to work for 6 or 9 months, and the prospects of getting something are not sure, so you need really some steady engagement. My last remark would also devote to the fact about budgeting. Of course, the Federal Ministry of Health in Germany has some budgets for international purposes, but following also a tradition, they are rather limited, and therefore it's also necessary to liaise with other institutions. And we are glad that this was successful. For instance, the European Union has, I think, some 8 years ago financed the simulation training center at the Medical and Pharmaceutical University of Chișinău. It was something which has already been prepared in the German-Moldovan cooperation, and I think this was something which really strengthens something which is already strong in Moldova, and this is quality of medical and professional training in that regard. With these short remarks, I just wanted to highlight the prospects that also bilateral cooperation can have. My professional work now is not so much anymore in the bilateral, but in the EU business, and I'm mostly doing pharmaceutical policy and pharmaceutical legislation in the EU. But also in Brussels, we still have some contacts just to liaise Moldovan initiatives with the appropriate EU bodies, and in that regard, I'm happy to offer that we can follow up Moldova in that context. So thank you very much. Wishing you best luck for this conference, and all the best.
Thank you very much for good wishes and good program for the future, which we shall realize all together. Actually, what should told us, this is the program which we step by step try to realize, to push in our life in different areas. Emphasis, because I insist, but Humboldtiana are in all areas of scientific activity. We have Humboldtians, as I told, in history, in mathematics, in chemistry, even in archaeology. I believe that in nearest future we will have Humboldtians in medicine. It is necessary. With your instructions, it must be done. That's why our Humboldt Kolleg will be start for a new collaboration, and in this year of Alexander Humboldt, 250 years birthday, it is the real time to think about the extension, collaboration in frame of this very good program, because it doesn't exist anymore in Humboldtiana. One time Humboldtiana, long life Humboldtiana. Thank you very much, and now we will start our scientific work, and the first talk will be done by Director of Max Planck Institute, Stuttgart, Professor Bernd Heimer, our colleague. We have agreement of collaboration many years, and we collaborate and are doing together research in area of functional nanostructures. And the talk, which will be presented by Professor Gerhard is Spin and Charge Relations in top-oxide nanostructures, and maybe more general. Thank you. Let's take this.
Do you need a microphone? You can sit and talk.
Oh, no, I'll stand up. So, good morning, everybody. First, I would like to thank Professor Sidorenko and the organizers of this conference for the invitation. Professor Sidorenko has been to Stuttgart several times, but this is the first opportunity for me to visit his home institution, his home country, and I'm very much looking forward to interacting with him and his group and with all of the attendants of this conference. I also need to apologize because I realized too late that I was going to speak in this very general session that is attended by specialists in various disciplines, including medical doctors, etc., as we've just heard. So I gave a title and abstract of my talk, which is very specialized and more targeted to an audience of physicists. But since I realized that I was going to speak here in this general session, I have taken some slides from some public talks I usually occasionally give on quantum physics, and I'll try to motivate our research to people from various walks of life, so that you won't get bored by what I have to speak about. I apologize to the experts who will not learn much new from this talk, except perhaps at the very, very end. So what I'd like to do is I'll give an introduction to what is today often called quantum materials, and I'll explain what we mean by this. And then I'd like to specialize to two particular types of quantum materials, namely ferromagnets and superconductors, which are also the subject of this conference later in the week. And there are sort of two systems that I touch upon. One is elemental magnets and superconductors, and then a more complex system, namely metal oxide nanostructures, that I will cover at the very end. Okay, first I'd like to thank the collaborators. We work together with Professor Sidorenko, as I already remarked, and his group, but then also various groups in Russia. These collaborations are brokered by my co-worker Yuri Khayrukov, who will actually speak later in this conference. And then at the end I will also talk a bit about metal oxide nanostructures that we investigate together with the group of Christian Bernhard from the University of Fribourg in Switzerland. So, by way of motivation, let me just tell you a little bit about everyday life, where you encounter various forms of resistance in weather conditions, in traffic, etc. And this is, of course, very annoying. And sometimes people dream of escaping to outer space, where things, the planets, stellar bodies move without resistance across the vacuum space, but then they realize soon enough that even in space there's a lot of resistance. There's growing space junk here in the Earth orbit, but also if you go to outer space, then there's violent events such as supernova explosions that give you a lot of resistance. So escaping to space is also not a very good way to avoid resistance. But then when you look at very, very small scales, namely in atoms, it turns out that the electrons in an atom move around the nucleus without any resistance at all, right? So, and that's a good thing, because if they encountered resistance, the atoms would not be stable, they would collapse, and we wouldn't be able to exist. Now, why is that? Why are electrons and atoms able to move without resistance? Well, that's due to the wave nature of electrons. Okay, so the electrons have a wavelength that is inversely proportional to their mass. And the wavelength of the electrons is comparable in dimensions to the orbits of the electrons around the nucleus. Right? And then when you look at the wave-like motion of electrons across the nucleus, around the nucleus, it turns out that these electrons can form standing waves that are perfectly stable. And that's a consequence of quantum physics. Right? So without quantum physics, atoms would not be stable, and we wouldn't be able to exist. Now, of course, in reality, this was sort of a cartoon. In reality, these waves around, of electron waves around the nucleus are three-dimensional, and they're called orbitals, and some of these orbitals are displayed here. The meaning of these images here is the following: the square of these waves basically gives you the probability of finding the electron in a particular location of space, and the colors there are the different signs of the wave function. So they could be positive and negative, and these signs of the wave functions are also important for the chemical and materials properties. Okay? Now, in materials that we are investigating as solid-state physicists, of course, these atoms and the corresponding orbitals form regular arrays. And again, the stability of these materials, regular arrays of atoms, is governed by quantum mechanics. If quantum physics didn't exist, all of the materials would collapse. So, there's various quantum effects in materials that are very well known and very well understood for more than 100 years, and that we use in everyday life. For instance, the absorption spectra of materials that have these sharp features here are governed by quantum mechanics, and they are, of course, they underlie the functionality of materials such as dyes, light-emitting diodes, etc. Okay? So quantum effects in materials are very well known. Quantum physics underlies the stability of all materials. So what do we actually mean by the term quantum materials? Isn't that a tautology? Isn't that some completely meaningless combination of words? Well, in some sense it is, but it turns out that there is a well-defined meaning to it, namely what we investigate in the area of quantum materials, so the macroscopic motion of conduction electrons. And this turns out to be governed by classical physics in most materials. So even though the electrons are waves, these waves form little bundles that are incoherent, and they bounce off defects in the solid, just like classical billiard balls, and cause a lot of electrical resistance. Okay? Now, it's been known for more than 100 years that one can actually obtain dissipationless transport of electrons in solids, and in some sense this can be viewed as a macroscopic extension of these perfectly stable electron orbits in an atom. Okay, and there are basically two ways of accomplishing dissipationless transport in solids. One is so-called entanglement of the electron wave functions. This is sort of pictorially represented by the rubber bands that are entangled, so that you cannot separate them, even if you stretch them. And the other mechanism by which this transport can be created is a bit more complicated. I won't touch on this at all. It's given by the mathematical discipline of topology. and that's illustrated by this rubber band with a single surface, and even if you stretch, so if you twist the rubber band and reconnect it, you get a band with a single surface, and even if you stretch it, the number of surfaces in this rubber band doesn't change, right? And by analogy, some of the topological properties of electron waves and atoms don't change if you stretch these waves to macroscopic dimension, and that also gives rise to displaceness transport. Now, one of the subjects of this conference and of this talk is the phenomenon of superconductivity, which was discovered in 1911. So it's been well known and well studied for more than 100 years. And this is manifested in the electrical resistance that changes as a function of temperature. In ordinary metals, it saturates at low temperatures and settles to a finite value. But in some metals, such as mercury or lead or niobium, the resistance vanishes completely below a so-called critical temperature. Critical temperature is just a few degrees above absolute zero in elemental metals, but it can be much higher in complex materials that I will cover in a few minutes. Now, what's the origin of superconductivity? Well, the origin is this phenomenon of entanglement of electron waves. So I showed you this picture here a couple of slides ago, where the electrons form little wave bundles that are incoherently moving through a solid and scattering from defects and impurities, causing electrical resistance. But in the superconducting state below this critical temperature, all of these electron waves form one single macroscopic electron wave that can sort of wind around the defects and therefore avoid electrical resistance. So it's a macroscopic wave function that extends over the entire solid, even though it may be centimeters, even kilometers in length, such as a superconducting cable. Okay, so that's the phenomenon of entanglement that underlies superconductivity. And of course, superconductors, since they've been known for more than 100 years, they have various applications. Perhaps the most influential application is shown on the left-hand side, magnetic resonance imaging. Even the medical doctors amongst you can relate to that. They're also used in high-speed trains, in particular in Japan. Some more novel applications of superconductors are in magnetic field sensors, for instance, for brain imaging, shown on the top right-hand side. And the subject of this conference is, possible applications of superconductors in electronics. And of course, electronic circuits, with regular metals and semiconductors, they dissipate a lot of energy, they heat, they need to be cooled. So if one could make electronic circuits out of superconductors, one can actually save quite a lot of energy. Now, superconducting electronics requires the combination of superconductivity with a different phenomenon that is also very well known, even known for a longer time than superconductivity, which is magnetism. But often people don't realize that magnetic order, be it ferromagnetic, where all the electron spins are aligned in one particular direction, or antiferromagnetic, where the orientation of the magnetic moments orients from one electron to the other, that's also a macroscopic quantum phenomenon. So it also is based on the entanglement of electron wave functions that leads to spontaneous alignment of all the electron magnetic moments. Now, if you want to know whether a material is a ferromagnet, of course, you can just measure in macroscopic measurements, magnetometry, but antiferromagnetism is much harder to detect because it doesn't lead to a macroscopic magnetic moment. So neutron scattering is actually a very powerful technique to image antiferromagnetic materials and even more complex spin field configuration that's displayed in this picture here. And the way this works is neutrons have tiny magnetic moments, right? They're also, just like electrons, have this sort of intrinsic an intrinsic spin that leads to a magnetic moment, and this magnetic moment interacts with magnetic moments inside a material. So, and that can lead to a spin flip of the neutron. And from exactly how, the way the neutron is scattered from the material, you can infer a lot of information about the internal magnetic structure. And this is done, this is sort of the basic idea. To realize this idea actually involves a lot of complex instrumentation. You need to extract a beam of neutrons from a neutron source and then spin polarize this neutron beam, monitor spin flip events, etc. I don't have time to go through all of this. This is just a picture of an apparatus that my co-worker Yuri Heidekopf has built at a neutron source in Garching in Germany that gives you some idea how such an instrument looks like. And I'd like to, in the remaining few minutes, tell you a bit about the work that we've done together on structures, nanostructures composed of superconductors and ferromagnets. Now, these kinds of nanostructures have also been studied for a very long time. Actually, the research on these types of structures was pioneered in Russia and Eastern Europe. So when this is, the simplest structure is shown on the top right here, where you have a sandwich of two superconductors and a ferromagnet. And it was shown by transport experiments some 20 years ago or so that the sign of the macroscopic wave function in such a tri-layer can actually change, analogous to the sign of the wave function in atomic orbitals. And this is a consequence of the ferromagnet that is sandwiched by the two superconductors. And such structures can actually be used in superconducting electronics. So you can sort of trap magnetic flux in a ring composed of such a structure, and you can move the magnetic flux around, and that can actually be used in a new type of electronics that in principle is actually completely dissipationless. Okay, so, but of course, if you would like to know the internal magnetic state of such structures composed of superconductors and ferromagnets, you need to apply a technique that is sensitive to variation of the magnetic fields on the nanoscale, and neutron scattering is actually one such method. And we've used neutron scattering to actually probe the magnetization of such tri-layer systems together with collaborators in Russia. And when you apply a magnetic field to a superconductor, the ordinary response of a superconductor is the so-called Meissner effect. So the superconductor actually expels the magnetic field. That is also very well known for almost 100 years. In such tri-layers, superconductor, ferromagnet, superconductor tri-layer, there are basically two types of Meissner effect, depending on the thickness of the ferromagnetic layer. If the ferromagnetic layer is very thick, the two superconductors actually expel the magnetic flux separately, right, and incoherently. But if the ferromagnetic layer is very thin, there's a so-called proximity effect that couples the two superconductors together so that they actually act as a single macroscopic quantum object and expel the magnetic field coherently across this tri-layer. And so we've recently been able to actually detect this effect, not in a tri-layer, but in a superlattice composed of superconductors and ferromagnets. This, on the left-hand side, you see the neutron scattering signal from such a superlattice. I don't have time to explain the origin of these peaks that you see, but suffice it to say that the sharpness of these peaks indicates the quality of the superlattice, and from the properties of this diffraction pattern, and its dependence on the neutron spin and the magnetic field, you can actually extract the magnetization profile of this superlattice, and it turns out that for this particular superlattice, we have actually coherently coupled superconducting layers so that you get a single macroscopic flux profile across the entire superlattice. If you expand the superlattice, you make the thickness of the ferromagnetic layers larger, then you can also observe the transition to this second type of Meissner response where each individual superconductor acts incoherently to expel the magnetic field. And together with Professor Singorenko, we've also applied neutron scattering to more complex multi-layers composed of superconducting niobium and ferromagnetic cobalt that can be used as components of electronic circuits. Okay, and in the remaining couple of minutes, let me just address an additional subject that is of interest in my group, which is high temperature superconductors. Of course, if you'd like to actually develop functional superconducting circuits, it is very difficult to use elemental superconductors with just a few degrees as critical temperature, because you need to cool these circuits, and in cooling the circuits you need to use more energy than you save by operating the circuit. So, and in this sense, a great opportunity arose about 30 years ago with the discovery of so-called high-temperature superconductors. They are more complex composite materials, so they're more difficult to handle, more difficult to understand, but they have the great advantage that they can operate above the boiling point of liquid nitrogen, and therefore can be much more easily cooled than elemental superconductors that have to be cooled with liquid helium. Okay, and we have for the past few years tried to develop some superstructures, nanostructures of these high-temperature superconductors. Here's one example. Yttrium barium copper oxide is one particular high-temperature superconductor, together with metallic ferromagnets. So these are analogs of the superconductor ferromagnet trilayers and superlattices of elemental materials that I've just shown you, but now using these more complex materials that have much higher transition temperatures. Okay? Now, we've learned over the years that working on these materials is much more complex than in simple materials, and I just want to, in the remaining couple of minutes, give you some idea of this complexity. One effect that is irrelevant in elemental materials is the transfer of charges across the interface. This is because this is a general phenomenon because the binding energy of electrons in the two materials is generally different, so electrons can migrate across the interface, and this is important in these materials because as a function of electron concentration, the two materials have complex phase diagrams that comprise both superconducting and magnetic phases. So this is displayed here. I won't go through the complex phase diagram. Just as an example, on the left-hand side, you see the phase diagram of one component of the superlattice, yttrium barium copper oxide. That is a superconductor for one particular electron concentration, but if you just take 0.2 electrons out, then it becomes an antiferromagnetic insulator, denoted by AFI on the left-hand side of this material. And conversely, the metallic ferromagnet can become a charge-ordered insulator when you change the electron concentration. And that gives rise to a fascinating variety of these complex phases inside a nanostructure that we've been able to elucidate over the last few years. So this is, for instance, one single yttrium barium copper oxide layer that is sandwiched by these two metallic ferromagnets, and you see that so over a distance of a few tens of nanometers, the phases of the high-temperature superconductor change all the way from an ferromagnetic insulator at the interface to a high-temperature superconductor in the center of the layer. And this type of phase behavior can actually have some fascinating macroscopic consequences. This is, for instance, the resistance as a function of temperature in a tri-layer of a particular manganite and a high-TC superconductor. And you see here, in zero magnetic field, this tri-layer is actually insulating. So the resistance goes up as a function of temperature, becomes very, very large at low temperatures. But then when you apply a magnetic field, the resistance goes down, and actually this tri-layer becomes superconductor in a high magnetic field. And this is sort of completely the opposite of the classical Meissner effect. It's also very unexpected. And the reason why this kind of nanostructure displays this very strange macroscopic behavior is not completely understood, but we believe it's due to the fact that this manganite layer can also exhibit charge-ordered insulating phases that sort of imprint themselves on the superconductor across the interface, induce a granular superconducting structure in the high-TC superconductor, and then when we apply a magnetic field, the charge order in the manganite is obliterated and superconductivity is restored. So that's just one example of interesting macroscopic behavior that can arise in these complex nanostructures of quantum materials. As an outlook, I told you in the beginning, in the introduction, that you can also use the topological defects in magnets and quantum materials in electronic circuits. This is called spintronics, and that's the subject of this technical session at the conference later in the week. This is just a couple of examples of what we mean by spintronics. For instance, you can have domain walls of ferromagnets, and these domain walls can move around in an electronic circuits and transport information, store information. You can also have more complex magnetic defects, such as this structure on the right-hand side, known as a skyrmion. That's sort of a knot in the magnetic structure. And you can use the transport of these magnetic defects to drive electronics. And the outlook that people are going to explore in this conference is sort of a combination of superconductors and these spintronic elements in future electronics. So this is, at the moment, it's basic research, but it has the potential over time to lead to a new type of electronics and a new type of transport of electricity that can sort of extend this dissipationless atomic orbits from an atom all the way across materials, and perhaps in 100 years or so we will have actually a network of superconducting cables extending all over the world. And of course that this kind of vision fuels the research in this area of quantum materials. Of course, on the way to this vision, a lot of fundamentalist research is required, and this is what we're here for. And this is the subject of the conference, and I hope that by collaborating on these issues, we will make some progress in realizing this vision over the next decades. So thank you very much for your attention.
Thank you very much. Questions, please?
Third question. You mentioned several times about superconductivity and practical usage. For me, it's not clear to understand. Superconductivity needs very low temperatures. Even high temperature superconductivity is very low. From other side, you send some slides about
Yeah, that's of course a very good question. Now, you're right, superconductors need to be cooled, but the very attractive features of superconductors is that you get if you feed electrons, if you feed a current into a superconducting circuit, it's persistent, so it never decays, right? So you need to make sure that the circuit is cooled, but then the transport of electricity in the circuit does not require an additional energy, right? And for instance, in a magnetic resonance imaging instrument, you find them quite a lot in hospitals, so they're actually of practical use. Inside these MRI machines, you have persistent currents that never decay. All you need to do is you need to just make sure that there's a sufficient supply of liquid helium or in the future liquid nitrogen. If you ran these machines with ordinary metals, resistive magnets, you wouldn't have to supply the coolant, but you would have to constantly feed energy into the circuit. And the trade-off between these two actually pays off in many cases, including MRI machines and also high-speed trains.
Okay, thank you.
Other questions, please? Actually, what Professor Kramer explained, it is reality. In China, it does exist many years. In reality, it is German project Maglev, which German developed, constructed, proved, but from noise regions, from grills, they stopped this project, and China just bought from Germany and put, and 10 years it does work. It is not a science fiction, it does exist in reality. And other applications wait for time, especially it is very pleasant to listen to the perspectives for pragmatic spintronics, the part of talk of Professor Kramer, and this is an absolute new area of activity, first of all developed by theorists. Here are presented the theorists, Professor Goldberg, Professor Vinokur, who started to develop theoretical base. And then we as experimenters developed this area. That's why it is the future. Strain in China, it is reality. Spintronics, it is the nearest future. Some more questions, comments? And maybe Professor Vinokur has some comments about spintronics. In his talk, he will prolong it. Thank you very much once again. The next talk will be given by President of Chemical Society of Poland, Professor of Toruń University, our colleagues, and President of Humboldt Kolleg, and many years friend of us, Professor Boguslav Bushevsky, Nicolaus Copernicus University, Poland, bioanalytics from micro to nano dimension. It is also general of interest. It will be interesting not only for chemists or physicists. I believe that it will be interesting for the whole audience. Thank you. Thank you.
So I'm sorry from technical problems. Okay, it's not working. What do we must do?
Can you start it? Try to start it.
Oh, it's okay. So, thank you very much. Good morning, ladies and gentlemen. It is a great pleasure again to be here and to have the possibility to present some interdisciplinary approach dedicated to nanotechnology, nanocomposites. I would like to thank Professor Sidorenko for inviting me and to giving the opportunity to present some of our results. Yes, I will be talking a little bit about medicine, because our life is connected with medicine. Unfortunately, this is not so good approach which God gave for us. So we all the older we use the medicine, and we needed some new materials. So I'm a chemist, I'm an analytical chemist, I'm working in physical chemistry also. So my interest is to look for the nanotechnology to apply some new materials which give for us the possibility to interpret some phenomena we are taking place on the cellular level. So this is the approach of our interest. Of course, everything starts in separation science, in particular in chromatography investigation, from two very important guys. One, it was Walter Nernst, who introduced for us the thermodynamic interpretation of some equilibrium in life. And another one, it was Michał Cwiet, who was a Russian professor working in Warsaw University and introduced for us chromatographic approach. So two very important things which give for us the possibility to interpret some phenomena on qualitative and qualitative level. From this point of view, we are looking for modern life chemistry for interpretation of some processes we are taking place on the border of different elements of our life conditions. Second one, it is of course miniaturization and a small sample which we use particularly for medical treatment. So I'm talking about new drugs, for example, biological active compounds. The relation between biology, chemistry, medicine, phytochemistry sometimes, so biological active compounds in general speaking. From this point of view, we are looking for interpretation of some relationship between, for example, microbiology, because we are using some pathogens, we are working with pathogens, we have in our body, unfortunately, 2 kilograms pathogens, but some of them, they are positive, some of them, they are negative. And of course, we are looking for some toxins which strongly influence our life conditions. From this point of view, we are looking also for some synthesis of biocomposites, which give for us the possibility to utilize as antidotum in opposition to such interest, so looking for those microorganisms, pathogens. From this point of view, we are talking about biocolloids. So this is the solvated elements which are in our human body, like in stomach juice, for example, and infection. So that is the problem. From this point of view, we are looking for bioanalytics. How to introduce new materials which give for us the possibility to determine, from one point of view, such toxin or pathogens. Generally, we are talking about determination, very fast methodology, because normally the medical doctor knows that people are use the microbiological classical methodology 70, 80 hours. For us, it's absolutely necessary to use very fast methodology, 10 minutes, for example. So for such interpretation, it's really very important. And they give for us the possibility to utilize, so for medicine, new approaches, for example, new drugs, clinical application, what was presented here, because people are needed some new medicaments. We want to live long time, and better, particularly women, beauty, and so on. So from this point of view, we are looking for the challenge between biology, chemistry, phytochemistry, for example, medicine. So for the new drugs, for cosmetics, for supplements also, and also for new type of foods which we use. So this is, of course, on the relationship between cellular inside, outside level for interpretation of such phenomena. So from this point of view, we are looking about bioanalytics, and that is a relation between synthesis and analysis. This is together, should be, and some people should be work together. Chemists, biologists, microbiologists, medical doctors, bioinformatics, for example, engineer, because they build a new equipment which give for us the possibility to interpret of some results which we obtain. So multi-interdisciplinary approach for the realization of such stuff. So we are talking about sensitivities and selectivity and strategy. Strategy from the point of view of determination of some metabolites. So for the compounds which are in the cellular level, we are talking about the metabolite, but if you have in the all organism, metabolome. So for this one, we are using hyphenated techniques like gas chromatographic investigation coupled with mass spectrometry or liquid chromatography. Also different another spectroscopic technology which give for us the possibility to obtain some signal and interpretation of such signal, which give for us the possibility to realize our concept. From this point of view, we are looking for the strategy related to selectivity, sensitivity, and reproducibility. For medical diagnosis, it's very, very important, reproducibility. So this is not chance to, because we have different matrices. We have tissue, we have blood, we have urine. So there is, on the basis of such matrices, we must to determine our compounds. So the range is very big and wide. So molecular mass give for us the possibility to utilize different technology, but still column is the heart of our system, because here are the processes for separation, for interpretation of some phenomena, for determination of gases, monomers, polymers, virus, cells, particles. So there is possibility to utilize of very wide range for interpretation of such data. Miniaturization is of course connected with the reduction of parameter diameters, for example columns, from 4.6 millimeter to nano scale, 60 micrometer or nano particles. So this strong reduction gives for us the possibility to interpret such efficiency, higher efficiency, so higher resolution and selectivity, but also pressure drop. That is very important because we are using some long or short columns depend on the diameter, and that is important for the changing of some separation conditions. For this point of view, we are looking also for the new materials, like 5 microns or nanomaterials, based on different support, like porous carbon, porous polymer, porous silica, nanoparticles, fiber, cheap technology. And the material has different interaction groups, and they stimulating natural membrane. So then on the basis of such one, elements like cholesterol, phospholipid, for example, there is possible to observe which processes are talking on the border, brain, blood. Brain, blood. So the introduction drug and distribution of this drug in human body. That is very important from this point of view, from medical diagnosis. So the diameters for the columns are really, really small. The advantages in miniaturization is, of course, reduction of some chemicals. And there is, of course, infrared of green chemistry. So this is the ideology. But also possibility to utilize different type of detectors, so that, which give for us the possibility to interpret some phenomena. Also unification, the possibility to utilize of such column for different technology. One column for different technology, like liquid chromatography investigation, supercritical fluid chromatography, or capillary electrochromatography. That is very, very important, because we are using the same materials for different techniques, and then we verify the results. So this is the comparison of some results. This is not one result for another technique, another technique, another technique, but this is the same material for the same technology. So like this one, we are looking for the significant drawback, which is connected with packet capillary, and when we are looking for the particles, for example, 60 micrometers, or formatted packet in the quartz column. So then we compare with monolith. We create porous structure stimulating bonds, for example. So with different structure, so like spongy structure or globular structure, depend on our interest. It is, of course, connected with pressure drop. So, and on the basis of this one, we have formed such structure in results on multi-step reaction. The multi-step reaction using, for example, polymers or silicon, ethoxysilane, methoxysilane reaction, give for us possibility to modify the surface of the quartz capillary like this one, and then to functionalize of the surface by blocking of the hydroxyl groups and formation of some attached center, which are modified using different porogen materials or polymerization initiator. In results of this multi-polymerization steps, we obtain material with high surface and without micropores, containing mesopores, and with very good permeability, containing only macropores, so cylindrical forms of the pores. That is really very, very important from the introduction of some new material like drugs, which will be distributed in the human body, for example. From this point of view, we are looking for the homogeneity of the bed format in results of such interaction, and then we observe very nice peaks, which give for us the symmetry, very sharp peaks, symmetry, when is the reaction done very well. If the reaction is in wrong conditions, so then unfortunately the surface is not homogeneous and there is material not so good porous. So in results of such interpretation, we obtain really nice material with strictly defined pores, and we know distribution of such pores, we know how is the pore diameter and how is the shape of the pores, which we use in our investigation. That is very important because the volume, total volume of channels is only nanoliter, 300 nanoliters. This is the very small one, but when we want to analyze some material, take it from the human body, for example, from brain, from stomach or tissue, this is only 120 nanoliters. This is a very small amount which we use for our investigation. And the methodology should be very sensitive because the limit of detection and the limit of quantity is very low here. From this point of view, we of course prepare some special unit set up that is of course connected with the special valve, which give for us the possibility to connect it, the capillary with very small another capillary, which give for us possibility to pre-concentrate our analyte isolated from the tissue. So that is the process of the concentration, and that is the process of separation when we use special type of material with special selectivity containing cholesterol groups. So this is elements which are localized in human well. So that is the one of these elements. So this interaction, such interaction, give for us possibility to interpret of those phenomena. From this point of view, we are looking for toxins, for example, which are not in wine, but in beer, for example. So there is mycotoxins, there is the preconcentration of mycotoxins, and there is determination of such compounds isolated from product for the beer preparation. So like malt, for example, and so on. And there is, of course, material with imprinted similarity, fingerprint materials, which contain similar groups like toxins, and then we introduce similar material here. So there is the similar to similar, the interpretation of such phenomena. Thanks to this interaction, there is sorbet on the basis of physical absorption and desorption processes in results of such phenomena. So this material was used also for very interesting approach. This is enzymatic reaction. So because when we have porous material, we introduce enzyme, which is sorbet physically, and then we put protein, for example, cutting of those protein, thanks to trypsin, for example, another one. So this porous material is coupled with this one, and then in results of such interaction, we obtain some bioreactor, which in results of the bioreaction with, for example, enzyme, cut it for us, our material, and give for us the possibility to measure elements for interpretation of such phenomena. So illness, for example. So big molecules, it will be not impossible to detect, but small one, there is of course possible. And then is obtained the fingerprint spectra on the basis of one characteristic ion is interpreted, and we know exactly which type of illness we have in our system, thanks to these specific materials. Another approach is, of course, connected with field for fractionation of some small particles, but also bioorganisms, like pathogens. For this reason, we are not using columns, but we are using chip technology, channels. When the separation process is done, it results to change of the flow rate. So we change flow rate of solvent, and then in results of this one, on the basis of this diffusion processes, it's possible to separate individual material. On results of such investigation, then it's possible to separate, changing the shape of particles. So then we have different type of particles, and then we obtain in results of different energy, surface energy, there is possible to obtain a very nice separation, fractionation of individual materials. From this point of view, we are using of such technology for the identification of separation of biocolloids, pathogens, using different type of detectors like capillary resonance electrophoresis, MOLDI, spectroscopy, and typical microscopic approach for interpretation of such phenomena. And there are the fraction obtained with UV detector and light scattering detector for separation of bacteria, and there is the two type of bacteria. So Escherichia coli and Pseudococcus. So there is possible to fractionate, depend on the shape of some bacteria. That is very important for the medical diagnosis, for the interpretation of such phenomena. So, but this is only one of the possibility. Another one, this is utilization electromigration techniques, and particularly using this charge localized on the surface of bacteria, because on the surface of bacteria we have different interaction groups, and then in results of differences of the charge distribution, there is possible to obtain electroosmotic flow. Stellan Huerten, he introduced capillary resonance electrophoresis as a separation technique for the changing of the charge on the side. We are using Smoluchowski equation. This is theta potential for the differentiation of the charge on the surface of different groups, and we use of this technology for separation of pathogens. So as the first in the world, we introduced of such technology for separation of pathogens. Thanks to this one, there is possible to observe how change the agglomeration and the repulsation of some pathogens in different conditions of solvent. So because the pH value and composition of solvent play important role here, because they influence the charge distribution of the surface. On the basis of such interpretation, be that special unit, this is capillary resonance electrophoresis, and fluorescence microscope as a detector for observation of bacteria, live or dead bacteria, because we are changing the conditions. So there is possible to observe how change the condition for the separation process. And then when we use fused silica, so no modified surface of capillary, there is no any separation, so no signals. We obtain some information that yes, separation is done, but without any information. When we modify of the surface, because we know how to functionalize of the surface, so then we obtain differences in separation process. So in chemically modified the surface, there is possible to obtain the special interaction groups which contain charge on the surface, for example, nitro compounds, toxic compounds, another one. So they give for the possibility to separate bacteria. And then in microscope we observe how move of this bacteria through the capillary, and that is possible to calculate how many bacteria we have in our system, and the results. So another question is how to interpret which type of bacteria is in done process. We observe that in results of such modification, there is possible to obtain during 10-15 minutes 8 different strains of bacteria, different type of bacteria. This is very fast methodology, very interesting for the quantification and information for medical diagnosis. From this point of view, we are using classical methodology because this classical methodology as a reference methodology for interpretation of such phenomena. We are using manual methodology, biochemical tests for 4 to 72 hours, and also serological tests, but also PCR, capillary electron, multi-TOF methodology, because they give for us the information during 3 minutes. So that is really very interesting from the medical point of view, particularly for infection and so on. So I know because we are working a long time in clinics with such approach. And of course, the MALDI spectrometer is used for the obtaining the reference spectra. So on the basis of this reference spectra, we compare the spectra which we obtain for our science. So we are building the library. So we have the special library for different type of bacteria, and then we compare of such bacteria and interpretate of our investigation. The library give for us the possibility to obtain also some selection of special type of bacteria, particularly bacteria which are in the milk, for example. So after the milk fermentation. And they are very interesting from the point of view of the modification of some nanoparticles, like silver nanoparticles, zinc nanoparticles, titanium nanoparticles, gold nanoparticles. The gold, the metal, is our support for the functionalization of the surface and formation of special type of bacteria in results of enzymatic reaction, because there is also enzymatic reaction done in results of such phenomena. So on the basis of this one, we obtain special type of support and then different type of amino acid and protein in results of biosynthesis. So microorganisms we are using for the biosynthesis of such elements. There are nanoparticles, and the surface of these nanoparticles looks like this one. So then we are using functionalization of such elements, and their reproducibility are very, very high. And in results of this one, we are started to control through the mass spectroscopy the formation, for example, lactoferrin built to the surface, or casein built to the surface. Also the MALDI for identification of sequence of amino acids. So everything is controlled in results of such investigation. We started also the kinetic. We know how fast is the process for the formation of such a structure on the surface. So in general, architecture of the surface of the, such materials. And results of this one, we of course, for us was interpretation, how is the binding, how migrated of this nanoparticle through the protein structure, and which one give for us the possibility to form of the bond between protein and the surface of the support. And then the results of our investigation, we found that the glutamic acid, aspartic acid, cysteine, and histidine, they are the centers which are fixed, bonded to the surface of nanoparticles. So through this amino acid, that is possible to obtain. Another approach, this is also catalytic reaction connected with anhydrase, so carbonic anhydrase and formation of nanocomposites. So then we have central atom, zinc, for example, or silver, and we have protein here, amino acid, and in results of supramolecular interaction, we are forming new type of drug, which we introduce to the blood and directly to tumor. So that is very important from the medical point of view when we know exactly which structure of amino acid we have and how format of such structure in results of this investigation. Using MALDI spectroscopy, using two-dimensional electrophoresis, Fourier transformation, and another technology, then we obtain the structure which contain different interaction groups, and we know how is the mechanism for formation of such a relationship and the format of multi-layer surface in results of such synthesis, biosynthesis, using catalytic reaction. So there is zinc is central atom. Sulfur play important role here because they give for us the possibility to fix it of this one, and in the results of them, then we coated such surface through the amino acid. The mechanism for the migration of such protein through the liver or to tumor through the membrane natural cell is going through the channels, but not only, because there we have hydrophobic, hydrophilic interaction. Through specific interaction, that is possible to migrate, interact with such tumor. So this is the medical interpretation of such phenomena. Of course, we are using triple quad, mass spectrometer, cutoff mass spectrometer, MOLDI, and so on for interpretation of such phenomena, because everything is very, very strictly controlled according to the protocol in clinicum, which is in clinicum. So, of course, there is only the small amount of our information regarding of this study. This is the beginning. We have the quite big grant at the moment project for the realization of such investigation, and we are realized in interdisciplinary and international team when I'm coordinator of such project for the interpretation of some phenomena. So maybe in the near future we found some interpretation and knowledge how change the relationship between the protein and tumor and protein and so on. But this is the future. And of course, I would like to thank my colleagues and co-workers. Also, one girl is from Moldova. She graduated by me, so Viorica Reilau, and she spent 3 years in my lab, and she wants to stay longer time, so she is as a postdoc. She is very good specialist in spectroscopic investigation, really very good, and she is working with pathogens also. And also to, I would like to invite you to Torun, beautiful, not so big, but beautiful city, and with very old history and very good gingerbread. Thank you very much for your attention.
Thank you very much, dear Professor Buchowski. Any questions? Please. One of your slide demonstrated images of great personality Marian Smoluchowski. We, who deal with documentation, knows that he is so famous like Cameron Honors, because the first liquid air, first liquid oxygen was done in Krakow by Marian Smoluchowski. But this genie has founded also another discipline. I see that in electrophoresis.
Electromigration technology, this is theta potential for interpretation of some phenomena, but he also, together with Einstein, interpreted the quantum chemistry, why sky is blue, for example, why some processes are talking in our life, and the relativistic theory. Unfortunately, he very young, 42 years old, he passed away.
Yes.
He was infected of some...
It was explosion. He prepared liquid oxygen, and it was exploded, and that's why he took area he gone away.
Yeah.
But he founded some new areas of activity. It is one example of how Humboldtian, for sure, he is one Humboldtian as well. Okay.
Thank you very much.
Thank you very much.
Thank you.
Now, let us give possibility to make presentation Professor Levchenko. Professor Levchenko, delay his flight. This way, he just called with some problem. So, let me introduce the presentation of Professor Levchenko. He will present a very interesting talk which can be useful for all scientists in each area of activity. The title of his presentation on the way to smart energy world, and he will present also one program of networking, which can extend our collaboration. So, please, Professor Levchenko, your presentation.
Thanks a lot, Academician and Professor Sidorenko. As usually, he organized a very interesting event like today, and I was few times in previous colleagues. It was as well very, very interesting and useful for us. So one more time, thanks a lot for organizing this. And unfortunately, my presentation is very far from spectronics, but nevertheless, maybe it could be interesting for somebody. So I named it On the Way to Smart Energy World, and you will understand why I name it a little bit later. My traditional slide is Belarus is here situated. It was a slide I show it every my report since maybe 10 years. When one time in Berkeley, I was asked from my neighbor, where are you from? I answered Belarus. He told, oh, I know it's near Mexico. Okay, but it's Americans. Now, you know, we are near Moldova. So I represented from very famous institute of Belarus Academy of Sciences. It names Likov Heat and Mass Transfer Institute. It's widespread spread of our investigations here, including energy and energy efficiency and so on. I would say that smart energy and smart technologies, okay, it's not a lot years ago, because politicians of developed and developing countries start to understand that their level of their intellectual level is not so far, especially in energy. And they decided to introduce special technologies like smart technologies. It depends usually of level of development of the country and mostly investment for modernization of energy grids. Some characters and characteristics of this technology shown is here. It's very, very effective technologies, and unfortunately there is no real smart energy grids used in the real operation. It's only mostly on the basis of pilot projects, and as well, unfortunately or fortunately, in the United States. And it's our ability in our institute is something like a special cluster, we name it. It's like artificial computer cloud. So we can make a lot of modeling, a lot of experiments, numerical experiments, using this cluster without connection to internet, because everybody knows now we have very, how to say, not stable world, and to avoid our characteristic of energy systems, to vent it inside internet, we use this cluster. It's maybe 5 years ago characteristics. Now they 2 times or 3 times more of cores and storage and so on. So it's only information. If somebody from us needs a nice facility, you can ask us and we can provide you this. So as well, there is a pointer. No? Okay. The last sentence is Tech Dome It's an invention of my team. It's a, I will show you a little bit later how it works. And we use it for modeling of our energy system and prepare the special pilot project. And now we wait for investment from our budget of our government. It's a scheme for that pilot project, and we use it for smart, so named smart houses, smart cities, smart village, smart islands, and so on. And due to that, as I mentioned, smart technologies now to fill in something like gap between reality for energy system and future development. In between, it's a very big necessity for investment for modernization. And as I mentioned, government of a lot of countries decided that smart technologies will save not only money but as well time to provide with energy all grow up the necessity in energy. So it's a little bit demonstration of our technologies. Oops, what? It's only cinema to demonstrate approach of our modeling. So you can use your mouse or others devices to create your own house, having normal structure. As well, there are some database inside with special characteristics of thermo characteristics. You can add real objects inside which influence for your energy consumption. Then you can add some external, like wind power generator, like electric storage, like charger for your electric car. As well, you can use smart water grid technologies. Then you can see through view, it's without roof because not to see inside. So your in nearest future house will consist of such elements, as well as smart elements. Then you can model what will happen if you make some changes. If you have, for example, some extra $10,000, you can invest in some to modernize your house. For example, you can change thermal resistance of windows. You can use modern windows. So you can make choice from database, insert it in your model. Then you can set outdoor temperature, for example, 5 here centigrades. Then you will see the results of your modernization, how temperature will change, how your insulation will work effective or not effective. And then then you can recalculate if you change for your heater, for example, on second floor. So this software tool allows you to model in more or less real situation your house. We name it smart house. If you would like to model something like smart village, you can make clone of these houses, make some changes in one of them, and make some special research separate in buildings. So it's a specific interesting tool as well, and we use it for as well very interesting project. The name is Smart AG. It was inside Horizon 2020. It was we used 2 test bed, Minsk, 2 buildings, multi-stop buildings, and city of Kalundborg with 10 or 15 cottages. And we use several special smart technological modules. And for example, using this cloud computer, I can, for example, control the energy consumption of in Kalundborg, sitting in my office in Minsk, and vice versa. And some illustration of this project, we can see as well additional cinema. We made some comparison here between, okay, it sounds like advertisement, what we can do using our smart technologies. It's normal district. We have three characteristics with not so good situation with energy consumption and environmental. Then we introduced our technology, and then we can see the benefits of this. You will see now comparison of two. One is normal districts and this smart district with smart technologies, and you see in every hour you will see the diagram of energy consumption. And using these technologies for smart technology, we can save approximately up to 10% of energy consumption. Taking mind it's billion of kilowatt hours, it's not bad amount of dollars, for example. I say it only for interesting as well, a word from Alexander von Humboldt. It's me here. 2 years ago, as well, Mr. Schwarz was president of Humboldt Club, and I was awarded of some of this Humboldt Alumni Prize, and we use this prize for, okay, I will return back, to develop this special platform. We named it HISON, Humboldt on the way to smart energy world. So everybody can use this platform to exchange ideas, projects, and so on. It's, I will show, maybe I will go to internet and because I cannot do it in parallel, unfortunately. So it's a specific usage of smart technologies and energy efficiency because of necessity to save energy, to save climate, and energy aspects have a big and important role in this activity. So it's okay, it's very interesting, and this networking initiative, Humboldt initiative on smart energy and network technologies, HISON. It's a short description of this platform, and it allows a lot to do between Humboldtians. Now this platform is more or less finished, and we are very urgently needs of comments and additions and corrections of Humboldtians and members of other programs to improve our platform in this more effective way. So it's short our approach for smart water system, because we decided that now we know everything about smart energy system, and now we try to use our knowledge for this smart water technologies as well, very important. And but we start this activity only last year, but nevertheless we develop a lot of services for cloud computer in like in for energy, smart energy technologies. And as well as yesterday, United States Summit start in parallel with our conference. Yesterday we opened our conference, and the United States Summit on climate. I only added this file today in the morning. So, okay, now it's our contact. Here, my contact, you can find it in our and I try to switch on to this. Aha. Oops. Unfortunately, it's technical problems. The system dislike our Apple. It's only Microsoft. But I return back. I try to show you our platform, I mean HISEM. So there are several possibilities to introduce yourself, to be the member of some of group. It's like LinkedIn. But as well, we add special service, name it knowledge sharing platform. Technical problems. And I will repeat my ask for everybody to help us to modernize this platform for interesting collaboration between Humboldtians of countries which are interested in this. I would say that several Humboldtians registered there, from Poland, from Russia. Unfortunately, we receive nothing. We only receive, oh, it's very interesting, we will use it, but nobody told us how we can use a more effective way. So I will wait for your response as well. Thanks a lot for your attention. Yeah. I not understand your initial words on your sentence because it's a little bit louder.
I repeat. Professor Kramer asked you, the smart house program, it is just prediction or does existing really system which does exist and you can give some calculations, numbers?
Okay. Thank you. Yes, this program exists and we use it several times, but only with our assistance. We not take it to the market because it's not very simple for ordinary people to use. But now we have interesting proposal and interesting idea for small city near Stuttgart, Rüdesheim, and they intend to make this Rüdesheim smart city. And they are interested in our approach, and we decided, right, maybe during this month we make special presentation there to make special portfolio from what measure we have to start. That's all. In addition, there are approximately 400 software tools promising some features like I described. Unfortunately, maybe 2 or 3 of them are more or less on the market for usage. One of them is Essence, a special program. A yearly license costs $40,000 1 year. And if you would like to make some special changes inside, you have to pay additional money. Our program now is like free, but we use in the projects and try to... Okay, thank you. Nice question.
Thank you. Actually, energy saving, this is a general problem, and for Moldova especially, it is very important for each country, for sure. But for a country which has nothing,
no energy
own sources, earth gas or coal and other sources, that's why 2 ways. One way was demonstrated successfully in Germany. In Germany, 10 years ago, started a big program. As you come in Germany, you can see nearly all roofs in villages are covered by photovoltaics. That's why, especially in South Germany. And it gives a big amount of electricity. And for such country as Moldova, where sunny days even more than in Germany, it should be done just now. But another way is not only using reproducible energy sources, but saving, not wasting energy. For this purpose, we'll do also the superconducting spintronics, because we will save a lot of energy which just is wasting and damaging the environment. That's why these 2 ways should be developed simultaneously, choosing another umweltfreundlich sources, renewable energy, and another, what is in your presentation, the smart house, smart transport, which will save energy, not to reduce consumption, actually. Thank you once again for presentation. And now the morning session is over, and now I ask all participants to go on the stairs in the front of the building. We shall make our traditional Humboldtian photo, general photo, on the stairs in the front of the building. After that, please go to the 2nd floor, these stairs on the 2nd floor. There will be lunch break. During lunch break, we will eat a bit and discuss a bit, and then you have possibility to discuss. Some reporters come and will ask you. That's why it is freiwillig. It is up to you. You can answer to the questions of reporters. It also belongs to our work, because visibility and publicity should be done also. And then to participants who have in their bag the invitation to the external session, it will start at 13:45, a quarter for 2, the same bus which brought you from Classic Hotel here will wait for you. Please take your seats in this bus. You will look in your bag, and 2 guys who followed us here, they have list of participants of the external session, and then take place after lunch break, take place in the bus, and we go to the external session. That's why our program for the second part of the day is clear. Now, please, we will go to the stairs, we will take a general photo, and then go to the lunch break. Thank you.